So this is the last day of the class. Excited? Right. Okay. So what we will do today is we will go over some of the important things I want you to remember, so that you know how to prepare for your finals. Okay. Speaking of the finals, I will make it available from the first day of the final, which is May 1st, until the last day of final, which is May 7th. So you can take the flexibility to finish it anytime within that period. But once you start doing that, you will be timed. Okay, you will be timed for 2 hours. Okay, you'll be timed for 2 hours, and it's open note. It's open note, and no group discussion. It's individual. It's individual. It has no group discussion. Yeah. If you have group discussion, you'd better turn into separate answers. I don't know if you can do that, but yeah. But I will tell it from your answer. Okay. So no group discussion. 2 hours. Open note. You can look at whatever materials. Okay. But actually, if you are not familiar with the materials, I believe 2 hours is not enough for you to finish the test. So yeah. So let's talk about what should we expect in the final. Okay, let's see. This is a midterm. Midterm is spring. No, it's week 7. So what before midterm is those. Let's see what is before. Okay. Okay, we will have a little bit stuff before the midterm covered in the final. So it's the proof. Okay. 2 kinds of proof. Remember that. One is indirect proof. One is direct proof. One is indirect proof. All right. So before we talk about proof, you may want to print this rules of inference. You may want to I think I printed for you and gave it to you. Maybe you lost it, but you can print this out. Rules of inference. Okay, that will help you to do a proof. Okay, direct proof or indirect proof, because every step in the proof you need to specify what kind of rules rules have you applied, okay, to transfer from maybe step 2 to step 3. Okay, you have to specify what rules have you used. Hey, come on. Okay. And for this proof, using this kind of template. Okay. Better to give you example to refresh that a little bit. So this is a template that still remember this. We have the expression specified here, and then we tell what kind of rule we applied and what is the thing we applied on. What is the expression we applied on? Okay. Well, let me put that into example. Using rules of inference. Okay, also you need to know how to transfer from the natural language to whatever you want to prove, like this: P1, P2, P3, Pn. And the conclusion is C, right? We want to prove C. We are given P1, P2, P3, Pn. This is the meaning of that. Yes. Over I say the proof in week 5. Let me see. It's a propositional calculus. Yeah, still get familiar. I think you know what is propositional calculus, what is predicate. Okay, propositional calculus includes those implies, and, or, those things. But predicate is returning true or false, and it also include greater or equal to, less than or plus. Those things are all included. I'll talk that later. But this propositional calculus. Okay, so this is a proof which is pretty complicated. It's only apply maybe one rule each step, but you can apply multiple rules at one step, as long as you specify that clearly. I mean, here it's like apply a common rule to number 9 expression, 9, right? But you can combine them to make them in one to save some space. That's fine. I'm fine with that. Let me go back here. Okay, so this is trying to say that this is trying to prove this is true. Okay, so that's the actually direct proof. We want to prove open or close, and open is true. So this is how we prove it. Okay, this is how we prove it. This is how we reduce it to open, but here is what we want to prove. Okay, maybe this is not a good example. Let me find something else. Okay. Basically, when we are trying to prove something, we are given an expression which we want to prove it to be true. Okay? If you still remember, we're given an expression. We're given a predicate calculus expression which we want to prove it to be true. Okay? And then start from this expression. You gradually apply different rules there, common and, common or, commute and, commute or, maybe different kind of inference rules. Then you gradually reduce that expression to true. So this is how it looks like at the end. Okay, no matter what you do, no matter what kind of rules have you applied, you have to reach here to true, from expression to true. That's how you do the proof. Okay, that's how you do the proof. The direct proof. proof. So this is an example. Okay, there are examples. Okay. So this is a whole example. Okay. So maybe I will give you a natural language description and you translate that to predicate to propositional calculus like that. Okay, like the PR. Okay. And start from the PR, you apply those rules, and last you prove that expression is true. Okay. That's the direct proof. Right? That's a direct proof. Or I may just directly give you some expression and ask you to prove that's true. Okay? But here is for this question we actually translate something into translate some natural language description specification into expression. Formal specification, okay, and prove that to be true. Okay, so that's the direct proof. Then for the indirect proof, okay, indirect proof, the idea is we want to find the conflict. Okay, we first assume that the conclusion that is not true. Then start from there, we find some conflict with the conditions we already know. Then we can prove that is true. Okay, so here, let's see. This is an example to demonstrate negation of channel open, and the conclusion is sender. So we are given that channel open is not true. Okay, we want to prove sender is true. So what we do is we first assume that sender is false. Right? By saying this, we are saying sender is false. The negation. Okay. Negate. And then okay. We assume that sender is false, and then we're already given that channel open is false, so negation of channel open is true. Okay, so that's given, and also channel open or sender is true, and then from these three things we already know, okay, we start to transform that into this like here sender or channel open. It's directly 3. Okay, and then we apply the common or, and then it becomes something like this. All right, and then we apply the PR2 and the definition of negation. We know that sender. We get the sender. And after that, what we continue doing is we mix this 3 with the PR1 and 3. Then we have a contradiction there. Then we can prove that what we assume is wrong. Okay, what we assume is wrong, which means the conclusion is true because we assume the conclusion is false, right? Then we know the conclusion is true. Okay, so go back and read. If you forget what to do, go back and read this example. It will help you to faster finish the final exam question on the indirect proof question. What's that?
What week was that under? What week was that under?
Oh, what week?
Yeah.
It's 6. Yeah, it's 6. So the proof and the indirect proof is in week 5 and 6. Week 5 and 6. Alright. And then after we learn this, we learn the predicate here. Okay, predicate. So predicate is we learn directly after. Okay, actually in week 8 we also did some exercises, a practice in the some alarm system. Yeah, we can look at we can also look at this example. And then it should be week 9. Week 9 is the predicate calculus, okay. Okay, to understand what the difference between predicate and the proposition. Okay, this is an example. So if all the valves are open, but at least one monitoring computer will be online, this thing is not doable, or like we cannot easily specify this specification with propositional calculus, right? If you still remember what is propositional calculus, it's the logic between and, or, imply, those things, right? And maybe if you mix them with true or false, you have those rules there. But here, predicate calculus, we have more we can do. We can do more with predicate calculus. Okay, we can do more. And we included a lot of other notations. Okay, like this. Greater, equal to, and all this implications still we can apply them in the predicate. Alright. Also we have this type of remember this. We have this type of structure, right? Which works like a function. So if you want to translate that, it's like computer 1 has a connected state to computer 7. Yeah. So this will return true if the computer 1 and the computer 7 is connected. Okay. So this got relationships, and let me show you another example. So this is another example of that structure. So it just specifies the relationship between the variables inside, between the two variables inside. Like this line has a line voltage. Okay, line has a line voltage. And the value is this active, and the line has a line state. The value is malfunctioning. Okay, and line malfunctioning. Their connection, their relationship is line state. And line and active, their connection, their relationship is the line voltage. And the computer 1 and computer 7 has the relations, which the relation means that connected, is connected or not. Okay. Like this, computer and offline, their relationship is state. So computer has a computer state. The value is offline. Okay. You can translate most of them this way. Right? So that's a structure. Besides that, we can also use this implication, implies, and or we can still use this logic. Okay, if you see that, here the reactor has a temperature. The value is the main reactor temperature. And if you want to put some restriction there, the main reactor temperature should be greater than 1000, which implies the monitoring computer is in the alarm state. Okay, remember this structure. This structure is like a function, but it's slightly different. It's slightly different than the function in the programming. So this only represents help you to know that the relation between these two variables within this structure. All right. Monitoring computer has a computer state, which is alarm. All right. The value is alarm. And when we're doing this type of question, most of the time, I will give you a description, a paragraph in natural language, and I will ask you to translate that into predicates. Okay, translate that into predicates. Yep. And you will definitely use this structure. So get yourself a little bit refreshed with this structure. All right. Okay. And something else in the predicate we need to remember is, okay, the ambiguities. Alright, so I mentioned that maybe a lot of times. So if I give you a sentence in natural language, okay, there may be different way to translate that. That means the ambiguity, because that sentence itself is unclear. Okay, the information conveyed by that sentence is unclear. It can be either way. So there are two ways to translate that. Okay, like or okay, like or kids love the mom, or kids love the mom. Okay, so here the mom actually it's ambiguous, because you don't know if the kid's mom or somebody else's mom. So all kids love the mom. Maybe love the mom who is a maybe hero mom in that story, so all kids love that mom. Or maybe all the kids, they love their mom. Okay, so that's sort of ambiguous. So there are two ways to translate that into predicates. Okay, with this quantifiers. If you still remember quantifiers, Let me show you. I cannot find. Can somebody remind me where do I mention the quantifiers? Like for R, for each. Like there exists. Yeah. Upside down A and reversed E. I'm trying to find which material is that. But that's something we will meet in our, okay, I think it's in set comprehension. Yeah. Okay, yeah, it should be here. Okay, so remember this. How do we specify that set? A set with this bar and this dot. Okay, what do we mean by this dot? The bar is a constraint bar, separates the declaration from the constraint, and the dot separates the constraint from the term. We need to look at the example in case you forgot. Like here, the dot after the dot is what actually inside that set. So here we're defining x as a natural number, and then in that set it's already x squared. So it's gonna be like 0, 1, 4, 0, 1, 4, 9, 16, something like that. Okay. Okay, quantifiers here. So the reversed E means there exists, or for some. Okay, so it's called existential quantifier, which means there exists. For example, here we put the reverse E, Y, which is integer, then x equal to y squared, means there exists an integer y such that x equals to y squared. Okay. This is another example. There exists a natural number less than or equal to 10 whose square is 64. Okay, what that means, n is natural number, and after this bar we have this restriction, n is less than 10. So there exists an n with less than 10, and also n is a natural number, which makes n squared equal to 64. Okay, so this is true, right? 8. It's 8, right? Yeah. So there exists, but if you use the universal quantifier here, that's actually not true. Like for Rn, which is a natural number, or the n less than 10, n squared equal to 64. That's not true, because only 8 make it 64. Okay. So here, reversed A says everything of a certain kind has a given property. Find quick. Okay, so this is true. for all the n which is a natural number, n less, for all the n natural number n that less or equal to 10, n squared less or equal to 100. Right? Okay, that's true. But if we put that n as the z, the integer, will that be true? Here. For all the n, okay, this is true because okay, n is from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of them are, the square of all of them is less or equal to 100, right? That's true. Okay, if we put like all the n, which is z, z means integer, okay, integer, which is z. If we say like all the n, z, n less or equal to 10, n squared less or equal to 100, is that true? Integer? Okay, how about the integer negative 100?
Well, it says integer less than or equal to 10.
Less or equal to 10. Negative 100 is less than 10, right? Right? If you compare minus 100, right? That's greater or equal to 10, right? Yeah. For the integer, because I changed that to integer. Negative numbers are integers, okay? So at that moment, that is not true. But for this expression, this is true. However, here I want you to get familiar with this format. So this is the quantifier for R, okay? It's saying for all the n that meet these conditions, we have this predicate to be true, okay? And we can also say for R and for there exists. Just remember this difference, okay? That difference. All right. Then we're reaching the z. Okay. Because we just finished that z. So for z, what I would like you to do basically is similar to the assignment. I will give you a description, and you are going to translate that into z schema, right? This schema, like this. Okay, I have a possible solution here. Mention that a little bit. Right, just remember. Okay, here. Any questions on this solution?
Second one.
Okay. Second one. You want me to explain that? Okay, for this I'm specifying a rental operation, right? A rental operation. So the input is category and person, because we are taking two input. A person who wants to rent a car, okay? What kind of category? And then output is a car, right? That part is not a problem. Okay, here we are going to update members, small cars, medium cars, large cars, those sequence. Okay, that's a sequence of car. Or you can just say we are going to update the car rental system, which includes all these variables. Then either way, it will work. But here I'm specifying I'm going to modify all these variables. Okay, no problem with this part. And then in the pre and post conditions, here members prime, because I'm using the delta sign there, which means I'm going to change that. So the members prime equal to members. That's that's the value of member before the execution of this method. Okay, so this prime means the value after the execution. Okay, member prime equals to member union this person, union this person. Okay, that means no matter this person is there or not, we try to put that person into that set. Okay, but since it's a set, it won't have a duplicates, so we can just do this operation. And then here in this line over here, okay, so this is a category. Category first condition, category equals to small, and small cars, that sequence is not empty. That's two conditions. That means if the category, the input category is small and small cars is not empty, okay, then what we do is okay, the here is output value. Output value is the output value equals to the head of small car, which is the first element of that sequence. Okay, I'm outputting the first element of that sequence, and then we do some other operation. Here is small cars prime equals to the small cars, and we remove the head. We remove the head of small cars. Okay, so we give the head, the first element of small car, make it output, and then we remove that from the sequence because it's already being rented. Okay, so this is how we remove. And here the car, the output car renters. Yeah, I shouldn't put this here. So then in the car, actually, I put that person into the renters list of that car. Okay, so the car dot renters union this person. Okay, so this is a set, and we are extending that set with this person. Okay, does that make sense? So which part is confusing?
For me?
Yeah.
I just didn't do the last part where it says remove head, small cars, and then wait. So
Yeah, because we.
Are you just using that as an example, or is that only true for small cars too? Like,
Okay, for small cars, and here it says same operations for medium and large category.
Okay,
Yeah,
so
you have to specify that as well. Yeah. So this is basically the conditions you have to meet after the execution. Okay. So the logic there, it says if you're renting a car, if it specifies this here, if you rent a car, you remove the first available car, right? This logic has to be reflected there and reflect here. This basically is a remove. We remove the head, which is the first element of small car sequence, from that sequence. Okay. And this right here is the return, right? Return is you return the car to the tail, to the end of that sequence, right? So basically this is if the category, we're doing the operation to the small cars, so we just put the small car sequence connected with a car. Connected with a car. Okay. So this notation means the concat. You concat the sequence. So this is available. There are many notations I didn't mention in class, but it's available in the references materials I provided in those folders. Most of the time you won't use that in the exam, but if you're writing a very careful this specification, you might need to use that like this notation. You want to connect this small car sequence with that car. Extend that sequence with a car. Okay, you return. And you do similar things for the medium and large sequence. Okay. So basically, I'm gonna do similar things here. Like, probably won't have that many questions, but I will give you a paragraph of the specification in natural language and let you to translate that into Z. Okay, specify that in Z, with Z. Okay. And also relations. Yeah, I forgot one thing to mention. The relations. It's week 10. Relations. Yeah. Relations here. So for relations, I will ask you some questions for the operation, like here. Okay, like we have relations, which is like the can access relation. Okay, John can access new files, robots can access new files, old files, summary files, right? Wilson can access text files. Okay, so this is a can access relation set. Okay, this is a relation. So I'm gonna give you some relation and ask you what is the value of the domain. What's the domain of the relation? Okay. Like for this relation can access, what is the domain? Tell me. What is the domain? Domain and range. Still remember domain and range? Domain is left element, right? So the domain is John, Roberts, Wilson, right? And range, how about range? Right set. Okay, what is the right set? Okay, so for this example, John new, Roberts new old summary, Wilson text. The domain is John, Roberts, and Wilson. The range, what is the range? Files?
Yeah, because it's users and then files.
The range is new, old, summary, and text. That's the range,
Yeah.
right? Yeah, that's the files. Yeah, that's the files. I'm asking what's the value inside that. Okay, like this. This is the relation like use this computer. Jones uses VX7, blah blah. Robots use sequent. Wilson use VX7. So the range of this relation, which names as uses computer, is these two computers, VX7 and sequent. Okay, so remember what is domain, what is range. I may ask a question about that. And how do you inverse? Yeah, here. How do you inverse that? So this means inverse. Remember this thing as well? This is inverse. Okay, so that's for the range, domain, the relations. And after that, for the Z, okay, so if you take a look at the introduction to the Z, we mentioned a whole bunch of things. Okay, for this belongs to union implied, this you're already familiar with, and some of the new things here with delta. What does that mean? That means you got change something, right? Okay, so if I give you this notation, you should be able to tell me what does that mean, okay? Like the delta and override, something like that, okay? Something I want to talk here. No, that's the example we've talked about already. Okay, so that's Z. We talk about Z. We talk about the predicate, translation, relations, proof, indirect proof, direct proof. Oh yeah, and last thing is the OCL. Let me see. So OCL, yeah, I will give you a class diagram. Okay, I will give you a class diagram like what we were doing in the last few weeks. We're using that class diagram, and I'm going to give you some of the logic of the class diagram to say what kind of system it is and some rules there. Then I'll give you some restriction for that system which cannot be modeled with the class diagram, like the value, like the age should be less or equal, the age should be greater than 18 to be a customer, something like that you cannot do with class diagram. So I will let you specify that with OCL, okay, something like that. And I will let you maybe specify operation which checks some value in query operation which checks some value from the system, okay? Like we are going to check the amount of customers of that program, something like that, right? And yeah, something like that. So, and yeah, and I may ask you to write down the operation and extend the class diagram with an operation, and then I will ask you to write down the precondition, the postcondition, something like that. Okay, precondition, postcondition in Z, and precondition and postcondition in OCL. Okay. Or so I will. Okay, remember the navigation stuff? Navigation. We navigation through the relationship between each of the class. So I'll give you a class diagram. I will just ask you, what is this relation? What does this navigation mean? Okay, we're currently in some context of customer. Okay, self dot self.card.color. What does that mean? Okay, that basically means the colors of the card this customer owns. Okay, the colors. If you have 10 cards, 10 different membership cards, what kind of color is that? It returns all that. Okay, so I will I will write a navigation there and let you tell me what does that navigation mean. Okay, like self.cards.color. Okay, or self.program. Self.program. Maybe that returns you all the program that customer participates in. Okay, something like that. Yeah, and then we will have a bonus, which is extra credit as the last. Is the last question. It's optional. You can take it or not, and I will not tell you what is that, so that you can have a surprise when you're taking the class, when you're taking the exam. Okay. So I think you should be able to finish that within 2 hours if you are pretty familiar with this material. If you're pretty familiar with that, 1 hour is enough. But if you need to look up something, I think 2 hours should be fine. Okay. So now it's time for you to ask any questions you have. So time is like available from May 1st to May 7th. Once you start it, you will have 2 hours. It's timed. Okay.
How many questions can we expect?
Okay. Yeah. So I can tell you, two proofs. One on Z, two proofs, one on Z, one on the OCL, one on relations, and let me see. I should have more. Oh, and the one on calculus. The predicate calculus, those kind of transformation. Okay, so there should be like 5 or 6, yeah. But that's not that like 5 or 6 questions. But under each question, you have different smaller questions point. Yeah, smaller categories there. So yeah, on those topics. 6 topics, and for OCL you will have just one class diagram, one system there. For doing a Z, you will only have one question on Z. I give you a specification of system, let you to do the Z specification, but there are also maybe short answers, short questions to ask you like something about Z. Yeah. Okay. Any other question?
You spoke about extra credit. Is it gonna be part of the? Is it gonna be under the?
Yeah, it's part of the test. It's part of the exam, final exam. It's the last question. Okay, if it's include the extra credit, it's gonna be 7 parts. Yeah, include the extra credit.
So extra credit will take about 10% or?
Extra credit?
Yeah, 20%.
Okay.
Yeah, right.
Yeah, it's gonna be 5 to 10%. Yeah.
So that means someone can get under.
That's 20%. That's two. Yeah. Okay, other questions? Or anything you still do not quite understand, you want me to explain that? Okay, I've already, yeah, there's a Z assignments answer there. And OCL, I will upload the answer of the OCL as well. So yeah, so that you can take a look at it. What?
OCL is not due yet.
Yes, not due yet. Yeah.
But if you upload the answer,
Oh, yeah, I will definitely upload after the due.
okay.
Right. Yeah. So, questions? Keep asking. Yeah, I know this class is not that easy compared with maybe intro of software engineering. Basically, you just remember all those concepts, right? But this class, it does requires a lot of mathematic stuff, logic, and your thinking and understanding to a lot of things. Yeah. Yeah, I mentioned that this course is basically the hardest one I ever take in my software engineering program. So yeah, but I'm happy to teach this course here in this semester because that help me to get my lot of memory back for this course and a good time when I was as young as you are. Okay, so yeah, if you do not have any question, you can yeah, start to prepare for the finals. And have you all registered for the fall semester already, or are you done with the program? I don't know. At what year are you in? In the master program.
Yeah.
Okay, cool.
One more semester.
Yeah, one more semester. Yeah,
Two more for me.
that's cool. That's cool. So yeah, hopefully I can see you again in some other classes.
Yeah, registered for the user interface engineering.
Oh, that's nice. Yeah, if you are not registered more class with me, then basically, I think this is the last time we meet in the class. So I wish you all the best for the rest of the study here and for the rest of your maybe for the starting of your career, finding jobs. Yeah, if you need any help, or if you think you have some topic or anything you want to talk with me, feel free to contact me or go to my office anytime. Or if you still have some question regarding the assignments or the solutions, okay? All right.
The presentation is due the 30th, correct?
Yeah. There's a date there. I set up all the date there, and yeah, don't forget to post the presentation and do an evaluation there, okay? Because I offer quite a lot of flexibility in this presentation as well as this final. You can take it basically anytime, right? So we don't have to stick on that plan, so that you can rearrange your priority on a lot of things. Okay, is that fair? Nice. All right, so thank you very much for the semester. Oh yeah, don't forget, please, I don't know if the evaluation has been over or not, so if you have a chance, please click on that link and put some evaluation there, feedback there. Yeah, everyone please do that. Yeah, course evaluation. Because because if I do not encourage that people to do that, only students with strong opinion will do that. That's gonna be terrible. Okay. All right. Thank you very much.